Hey, hello everyone. Welcome. I have a little scary moment. Literally everything crashed when I was playing the intro video. So I close off the browser. I'm open everything here. I see the countdown 3, 2, 1. But hey, here we are. Hello everyone. Welcome to another session from .NET and AI. My name is Bruno Capuano, part of the Cloud Advocate team. I'm here with Tanner. And hey, how are you, Tanner?
I'm doing pretty good, thanks.
It's a pleasure to have you here to also talk about something super cool. We are going to get there later. Do you want to introduce yourself? I know I'm the worst host ever. I need to invite people to talk about themselves, introduce. Please, Tanner, tell you a little about yourself, please.
I'm Tanner Gooding. I'm on the .NET Libraries team, and I am one of the owners and maintainers for all things numerics, math, hardware intrinsics, and tensor related in .NET right now.
Hey, that's super cool. That's super cool. And this is what we are going to talk today a little about. Not a little. We are going to talk about literally that, tensors and more. But before going there, let me talk a little about something super cool that should be live literally right now. And this is a repo that we have with this called awesome GitHub Copilot customization. There is I think that the .NET blog is coming now, literally now. I need to refresh the .NET blog and probably going to be here. Control F5, not yet, a little more. But the whole idea is that we have a repo where we are going to start to collect, and everybody's invited also to participate, make your pull request and more, to collect custom instruction, reusable prompt, custom chat models, and more. And it's super cool. I really, really like it. There is a set of a specific instruction example if you are working with ASP.NET that you can put in your repo or in your local VS Code or Visual Studio. And it's going to be part of the whole GitHub Copilot experience where you are chatting, doing agent mode and more. So take a look at this. I am going to share the link in the chat now. And it's part of what we've been doing these days. I think it was on Monday where we announced that, hey, the GitHub Copilot chat is open source also from the VS Code, so everybody have access to there and more. We really, really want to give the people the chance to know these tools, extend these tools, learn more, and do this, and do more. So if someone is interested, hey, I'm going to share the link and take a look. There are a lot of these, and I am not using them per se, but I pick up a little from the Bicep one and a couple of others into a main big one that I create for the repo, and it works, and it really helped Copilot to work better there. That said, as I said, I am taking a look at the comment right now. So hello, everyone. This is me. So hello, Radis. I am going to go for the full list. I also see some familiar names here. Tal, probably, if this is the Tal that I am thinking, probably coming soon with a super amazing topic and more. So besides this, the second one that I want to share is, remember this, we built this last time. And I know, kind of vibe coding, creating this space battle game or whatever. So the code is already there. If someone wants to take a look at this, you have access to the full video. And this is the main prompt that we created. Literally with one prompt, did 80% of the game, then the little iteration there. The final code is available in the GenAI, in the generative AI for .NET repo, so you can find everything here. And it's also have the current version that it can work with local models with Ollama or with AI models on the cloud. So you can even run the game. Let me see if I can run the game. This is the game here. Let me open my GPU there. And if I start to play the game and I play the game with Ollama, let me play the game with Ollama. There it is, playing with Ollama. We are going to start to see here how every frame, every movement, and everything else is processed locally. I think I am using 5.4 mini for this, which is very good, very nice. So if someone wants to take a look at this about also how you can play and do more, it's not very smart. It's kind of hiding in the bottom right corner. Come on, man, you need to go and kill the enemies and shoot the enemies. Okay, no, it's stuck there. It's fine. Which is, it makes sense. It's not, probably my main goal was stay alive when I create the prompt. And this is what it's doing. But hey, if someone wants to take a look at this, it's literally, again, open source there. And let me take a look at the Ollama. Yes, 5 Mini, also a great chance if you want to implement this using AI Foundry Local, which I have in my to-do list, or test with other models. We have all of this. So that said, I am going to go back to talk with Tanner about tensors, numbers, and more, and the current state of stuff that we have in .NET. What can you tell me? Can you tell us about this, Tanner?
So before that, I just wanted to say that I think both of the things you just showed off are pretty cool. I got into development originally because I wanted to make games, and I know a lot of other people that got into development for similar reasons. So it's really nice to see new ways that people can get started on trying to build things like their first game or integrating new .NET features into it.
Yes, and hey, you know what? Talking with people like you, which it came from with kind of a game background, the way that when we created the game, it was very simple. We basically have a large language model. We make a screenshot of the current frame of the game, we give it to the model, and say what I should do next. In this game, it's very easy. You can move right, move left, stop, or fire. So there are no much options. But someone told me, hey, these models are great. These models can do more than that. You can not only pass the current frame, but if you pass the current frame and the 2 previous, the model will infer, okay, this is how the ships are moving. This is how the bullets are going up or down. This is how you are moving, you as the main player. So it's going to give you a better reasoning, a better option, a better next action with some reasoning. And it really, really make a difference when we have another video where we explain how to do that. And it's great. And also, initially, when we started to do this, I take a screenshot of the console, literally, and save an image, a PNG image, and I drop the image to the model. But someone told me, that's heavy. That's processing, but that's heavy. You can store, if you want, the string because it's a console application. And pass the string, literally, space X, space A, the representation of the screen, what I am drawing in the console, to the model. And oh my God, it's starting to work probably 20 times faster. And it's a learning process, again, with the excuse to do a simple game. I never did games. I'm not smart enough. And then you can do something, learn, and more. It's kind of nice to do.
Yeah, I think it's a lot like anytime you're trying to learn or build something new, you have to start from somewhere, and everyone needs help. And, AI is just another tool in your toolbox that can be used to help get you started. You still have to augment it with your own reasoning. You still need to do trust and validation processes, but like using a calculator when you're learning math to help assert that you did the right steps and came to the right end result, it can just help accelerate and help provide additional validation and input, and it's just another tool to help you succeed.
Yes, and you nailed it, and that's the way that we are using AI. It's basically, literally, a copilot side by side, helping us and then taking a look, and for me, it's a learning experience. Oh, I can do this and I can do that. That said, I'm also aware that sometimes we have these crazy suggestions of stuff that doesn't make sense and more, but also learning because the model has some context, they have been training with ABCs, they know what they know, and so it's a full learning process. But if you told me, I don't know, last year that I was, not probably last year, but 2 years ago, 3 years ago, that in 10 minutes, I will have a fully functional game like this, ready to go with minor touches here and there, I say, no, now you have it and you're going to start to iterate and do and learn and more. I like it. It's part of the process. Yep. I see someone asking a question here about the repo. So this is it. Sorry, I did this one. So, and the repo, if you want to take a look at the code and more, this is aka.ms/GenAINet. This is where we put everything that we have there. So that's the one that you can find the mega prompt to create the game, and also a final version with all of the included version to play locally with Ollama, AI Foundry, more. And we use Microsoft extension for AI, but feel free if you want to extend this with semantic kernel or whatever. There it is. And I think I'm using Ollama Sharp for the Ollama part. I can't remember. But yes, that's cool. And yes, AI is here to help. So this is also the excuse to talk about how we are providing this new features into the framework and more. How we are doing that? I always like to see you and the other product team where they have this amazing discussion about the future of .NET, how we are doing and more. So how do we get here?
Yeah, so as with anything, it's kind of this iterative process, and you can't just put everything in box. You can't ship everything with the product. There's limited resources, there's limited time, and what ends up being crucial to the future of programming changes over time.
Yes.
Most often when you start with anything, it is this kind of niche domain where the people who use it may have this broad ecosystem within themselves, but outside of that ecosystem, you don't really see it much. And that's kind of where we were with things like AI or science or scientific computing or even deep math learning, 15 years ago. You had some semblance of things, but it wasn't really core or crucial at that point. And so you had all of these ecosystems that were building up their own individual products. You had Python, which really took off in this ecosystem when they started with NumPy and expanded that into eventually PyTorch. But that was really modeled and designed for and around Python. And every language is different and unique. The way you want to work with something in Python is a little bit different from how you want to work with it in .NET or how you might work with it in Rust or C or C++. Each language has its own nuances of what works well for that ecosystem and that language based on its own rules and paradigms and everything else. It's very similar to a spoken language and word ordering. Like how in English, everyone knows that it's the big green dragon, not the green big dragon. But most people, unless they're an English major, couldn't tell you the reason that ordering is the correct ordering. And in other languages, they have slightly different orderings depending on their own semantics. And so, it's very similar here. When a language like .NET starts working with that starts moving into one of those niche ecosystems, typically that starts by providing bindings over the underlying library. So for years, there's been projects like Torch Sharp, which provides bindings for PyTorch and allows you to access and work with the PyTorch APIs in .NET. But it's very much still oriented around Python. A lot of the idiomisms and everything else don't quite line up with the normal .NET look and feel. And so there's a little bit of give and take as people bring it up. Within the past few years, it's become fairly obvious that ML and AI is going to be a big part of programming moving forward. It is more and more important that everything provide a way to interact and access it. And so we started looking at ways we could do that. And we can't just go and do that and shove out everything that's existed for the past 15 years. We can't just say, oh, you don't need to use Torch Sharp anymore. There's always going to be code bases that just can't move off of it. They need to keep supporting it. They need to keep working. So you need to build something that works with both the old and the new. And generally the way that works is the .NET libraries team starts looking at, can we provide some kind of interchange type or contract that allows people to take the types from one library and use them more generally and start writing algorithms that are general purpose and work with multiple types. This is kind of similar to when we introduced span of T a few years ago. Span of T was the interchange type between both managed data and unmanaged data. So you could now have one API that would work with unsafe pointers or that worked with regular arrays. And over time, we have since expanded that to allow getting spans from more types of data. There are APIs hidden off because there are some nuances and dangers that you need to consider when using them, but there are APIs to do things like get a span from a list of T. There are APIs to go and get a span from a string or all these other types. And so span is really that interchange type that brings together all of the different collection types that we had over the 20 years prior. And so we start looking at how we can do the same thing for tensors. One of the obvious things you can look at is something like an interface that every type can go and implement, but there's some nuances with that. Some people are using they're using unmanaged allocations, and so there's lifetime considerations. Some people are using structs where they don't want to incur boxing overhead.
Yeah.
And so while interfaces can be a good option, they aren't necessarily the only option. And so what we ultimately ended up coming to is that tensors are fundamentally, even though it's this scary ML related word to many people, they're actually really just arrays. They're effectively this concept that says, I have data and I have a shape to that data. So a normal array has a shape where it's just a linear list of values. And then you've got multidimensional arrays where you can say, I've got an image and it's got 1920 by 1080 pixels. And tensors are kind of this abstraction over that says I can have my data and that data can have shape. And that could be something like an image. It could be multiple images. It could be basically any kind of shape that you want it to be, up to n dimensions. You can define what n is. And with that, we started thinking, well, we already have span as a way for representing one-dimensional data abstractly. And so we started building our new type, which is called tensor span of t, which is effectively span, but it also tracks the shape of the data that you're working with. So now you can work with multidimensional data. And because span has worked so well as the general purpose interchange type, we expect that tensor span will be able to fill the same purpose for this multidimensional data that you're working with in AI, ML, image processing, games, and many other scenarios. We do also still have an interface that you're able to use and implement on your types for when you do have more concrete things. And we expect that various libraries will provide their own ways to get a tensor span or implement the interface over time.
And one question, because I've been doing .NET for a very, very long time. I always put my age on the table so people know I am old. The light is good because you can't see my white hair right now. So these lights are very good. But on my 20 plus years of development and more, I switched from C# to C++, then did a lot of machine learning with Python and more. And the tensor scenario that you mentioned, I will say that are very specific, in the .NET community, the whole .NET community where we build big enterprise applications and more. I know that there are scenarios for tensors, but I will say that not everybody is going to use tensors like we use, I don't know, a string builder, in example, that is probably everywhere. That said, they're also very important because having those for those scenarios, which are probably not very popular, but they are there, it's really, really a key part of when we need to do some stuff there. I really appreciate the work that the team always been doing, trying to keep us to fill all of these gaps, big gaps or small gaps, but to fill the gaps there. But do you have the sense, do you have the feeling, and this is kind of a personal question, that there is a market for this, or we are going to put the tensor span, and 1 in 10 people are going to use it, and then it's going to be those stuff that are part of the framework and are not very popular? Or where do you think, I don't know, maybe in gaming, okay, people who are doing gaming and .NET, they may have some nice advantage now that we are starting to get there. Do you have any view about that?
Yeah, so
yes.
So I think that the important thing to remember is, like I just described it, tensors are just an abstraction over data.
Yes.
And so while one of the primary use cases is in things like AI and machine learning, people have actually been using tensors for years. They've just called it something different. So
Yes, you're
arrays,
right.
arrays themselves are tensors.
Yes.
They're just limited to being one-dimensional tensors. Anytime you open an image, you are working with a two-dimensional tensor. You are working with a 2D set of data. So you've got data that has a shape, both a width and the height, and so that makes it a tensor. When you're working with things like text, you can view that text as a one-dimensional set of characters, and so you have this one-dimensional tensor. But you could also view it as a 2D set of data if you were to say, I have this sequence of characters and these separators, such as white space, that break apart the words.
Yeah.
And so you have now defined a shape to your data to help process it as tokens to be able to better understand the intent or meaning behind that. And so compilers have fundamentally been working and doing tensor-like work for years when they are doing tokenization, syntax tree formation, transformations, and everything else. Even just opening your text editor and doing a search through it to find a match for a word, or doing a regex find and replace, you are fundamentally doing the types of operations that tensors underpin. It's just we've called it something different. And so really, I think while some things will continue to be very niche and specialized, and not everyone's going to go and immediately grab a tensor and start working with the data in the low-level foundations, you're going to find that tensors underpin everything in the code that we do. And because tensor isn't oriented just towards AI and ML, it's really about just performing mathematical operations on data. You end up using it to accelerate all of your workloads. You can use it for things as simple as, I want to compute the sum of all the values across this data set. So, you're doing that when you do enumerable.sum today in LINQ. Or when you're saying, find me the max value in this data set. All of those are things people already use with LINQ today. They're just doing it with one-dimensional data. And tensor makes it easier to give shape to that data and make it a little bit more powerful.
Hey, that makes sense. And yes, I haven't think about that, but yes, probably when I am using some entity framework functions or whatever to make my life easier working with my product database, deep down there, everything that's happened is using the latest libraries to make everything. Okay, I get the idea, and I really, really like it, because 5 minutes ago you mentioned something that is key here, that we've been doing this for a while, but we've been using arrays, we've been using other stuff that we didn't realize. So I like it. And by the way, a couple of comments that we have here. Pocket say AI in .NET. Yes, we're doing a lot of super cool things AI in .NET. Someone is also mentioning here that general relativity based on tensor. I will say strings, but string theories and more, but I'm not going to get there. My father is not here for then. And then we have a lot of people saying hi, questions about TalkSharp and PyTorch that we literally talk and more. So hey, it's super, super cool. And someone is asking, what libraries are we using? We are not talking about a specific library today, like we did in other episodes when we talk about extension for AI or Llama Sharp or others, but we are talking about mostly the tensors and numerics in the .NET. But I will share some links if someone is interested in how you can get some libraries to do AI that we have right now. Yeah. Which is not to do AI. I don't like the sentence. I will play my non-English speaker card there, but it's to maybe consume an AI model that we have in the cloud or locally, or maybe do something like that. But hey, it's cool. And we have Palpatine here saying, hey, in .NET, good. Yes, it's super good, super cool. That's why we are here. Sorry, Tanner. I wanted to give some love to the audience there.
Oh, of course.
People are asking about this. So we get there to a point that you and the team and the amazing people there, we get to, okay, we need to do something. We created a tensor. We have the tensor span. We have there. And as far as I remember when you explained this to me, this is our current .NET 9, have an implementation. We are working on that. And then we are going to do more for .NET 10. This is correct? Yes.
Yes. So in .NET, we've actually been doing some incremental improvements to just general numerics and math support for years. So, back in .NET Core 2.1, we introduced span. We also introduced mathf, which provided 32-bit floating point operations for available use, whereas previously we only provided them for double. We then, we continued adding new APIs and started working towards compliance with various standards and specifications, like the IEEE 754 spec, which defines how floating point is meant to work deterministically across machines. We continue doing that through 3.1, 5.0, and then in 7, we actually introduced a new feature called generic math. So in the system numerics namespace, there are a set of interfaces like iNumber of t and iBinary integer of t. These are then implemented by all the foundational types like int32, single, double, even decimal. And they allow you to now write generic algorithms where you constrain a t to one of those interfaces and you can just use operators. So you can now have something like a sum of t method where you then say, t.0 and you can do t plus t. You can now write all of that generically. You no longer have to write it for each type you want to support. And so that was a huge foundational step into allowing users to write more algorithms and do more with less code. In .NET 8, we started looking at what we could use and provide for accelerating existing user workloads. We'd been providing low-level functionality to have access to SIMD, which is single instruction, multiple data instructions, that every CPU has provided for the past, 20 to 30 years. It's been a fairly foundational thing that helped launch and make games on hardware possible, particularly before we were so heavily reliant on GPUs. And we'd provided access to that, but it takes a lot of knowledge and work to make that possible. So we thought, what can we do to make it so that the user doesn't have to write all that code themselves? And we started providing algorithms in Box, particularly via span, that allowed users to not have to write that code. They could just do something like enumerable.sum or span.sort or span.index of, and it would do the most optimal algorithm for you behind the scenes. Then we said, okay, we've done all of this, but we also need to be able to work with shaped data or data that isn't contiguous. Sometimes you're working with very large data and you can't load it all on your machine at once. You might have a multi-megabyte image that you've taken of the stars in the sky, or that the Hubble Space Telescope, takes pictures of. Those things are absolutely ginormous. And even GPUs have limits where they can only work with data that's so big. Most GPUs can only work with an image that's up to 16,000 pixels wide and tall. Anything bigger than that, and you have to change how you work with the data. You have to break it apart into tiles and start processing it differently. That way you can fit it all into memory, work within the limits of the GPU, and do the operations as needed. And when you just have a single contiguous allocation via span, you can't do that. So we started looking at, we need a way to work with shaped data. Everyone's starting working with tensors, and we started providing these new things called tensor primitives. So we have this class in the system numerics tensor namespace called tensor primitives that allows you to incrementally work with segmented or chunked data and allows you to do all of those same operations, but allows you to process it in a way that works for the data that you have, even if it's broken apart via multiple allocations, even if you're having to stream things off disk, it works with that data. You just have to write the algorithm yourself to deal with the segmentation of it. And from there, that was shipped in .NET 8, and it got improved a little bit more in .NET 9. But once we had shipped it in 8, we wanted to make a way so that users could not have to worry about dealing with the shape of the data themselves. And that's where we started working on tensor span of T.
Okay.
And so in .NET 9, we previewed as experimental the tensor span APIs. Now we previewed these as experimental because it is an absolutely massive amount of work to expose all of the support, to make it efficient, to make sure that it works with the various libraries and ecosystems that were already out there. And generally just get and hear feedback from the community to make sure that we're doing it right. And so that's why we shipped it as experimental in .NET 9. The feedback that we got was that things are largely in the right shape. There's these few little rough edges where we needed to work out usability, improve things, and generally make it better. And so we've been working on responding to and addressing that feedback in the .NET 10 timeframe. And as of a couple days ago, I actually removed the experimental attribute from those APIs, and we plan on shipping them as stable in .NET 10 this November.
Hey, that's super cool. And a friendly reminder to everyone here, every year we have a new version of .NET. I mean, that's the plan, and we've been doing the plan for the last 5 years or so, I can't remember. And the next one is going to be this November, .NET 10. But what I also like to remind everyone is that we can see right now the current state of these features. Everybody can collaborate, everybody can go take a look because this is open source, the .NET is open source. You can go to GitHub, take a look at this, create your issues. If you're not happy with something, ask your questions. We are trying to get feedback from the community, which is literally what you just said, and everything that came in .NET 10 is going to be kind of the final cooked version. And hey, I like when any of the product team remove the experimental label, because that allows me to avoid to add my code the pragma suppress whatever exception to use and test something. So I know it's literally 2 clicks or 2 lines that I need to manually write, but hey, I like what is there. But hey, it also means that the mature level, it's cool, it's there. And hey, thanks about that. I mean, I need, and this is a question that I also have, because I don't know if everybody is aware that when everything that you've been talking is not just implement this for .NET, but also the framework works in GPUs, CPUs, NPUs, and you have Intel, you have AMD, you have a lot of providers and more, and the .NET framework runs literally everywhere. I want to give this a try, an example in my Copilot PC when I have my NPU and see it's really using this and that. And I really like the way that today, and I only see this in a very high level, as a developer, I literally don't know anything about that. It's super well abstracted, super well presented that I am going to use it, and underlined is going to basically take advantage of the best resource to do that, which I really, really like when I am a developer, my type of developer who doesn't go deep for those scenarios. So, hey, it's kind of nice to have it there. And someone is asking that we need to provide Visual Studio 2026 with C++ 26 support. Okay, I am going to pass the question down to the Visual Studio team. This is not the C++ scenario, but by the way, I haven't done C++ in a while, but I didn't even know that we have that version there. But hey, happy to put there Tanner coding Captain America. Yes, probably because of the shield and more. I don't know. Maybe this is an AI screenshot analyzing what we are seeing right now. But hey, sorry, small pause there to basically say that. Do we got something to show that you want to show?
Yeah, so let me make sure I've got the
we only have 20 more minutes, and I know that we start to talk, and I really like Tanner and the super smart people that we have here at Microsoft when they start to talk how to solve this and that and more. It's super nice. Yes, not an AI, but maybe an AI man of peace here with a nice smile. But hey, I really like to hear about this, but I also know that people want to see some samples code and more.
Yeah.
Okay, let me bring you to the stage. There you are.
Yeah,
so we ask you to zoom a little the code, if you can.
Is that better?
Yes, that's better.
Yeah. So, like I was talking about, we've been working on building up these set of APIs for a while, and because we've been working on building it up and providing these layers, we provide access for developers to do everything from write the most naive code to literally to almost literally picking the instructions that the CPU will execute by directly specifying you want this SIMD instruction. And because of that, we've got this layering system and we've got options for developers. So like I was talking about earlier, you might want to write something like a sum loop that takes all the values in the input and computes what the sum of them is. And the most naive version of that is you define the result, you start it at 0, you loop through all of the values, and you return the result. And that's all fine and good, but it's also not very fast. And if you've got a lot of values, you might need to make it faster. So you're going to do the next thing that you might do is you're going to go and do what's called unrolling your loop. And this takes advantage of modern hardware features where the CPU, even though you're seeing 4 operations here, because they're next to each other, the CPU can actually execute multiple of them at the same time.
Cool.
So this, even though you're doing 4, most CPUs allow you to execute somewhere between 2 and 4 add operations at the same time. And so this will end up taking roughly the same time as one iteration of the previous loop. But since you're doing 4 of them, you're now looping 4 times less and you're getting faster execution overall. But you've had to write, significantly more code to handle that. But it's not even all the perf you can get. You might then want to say, well, I want to directly use SIMD. I want to take those 4 instructions and make them one instruction, but still process all 4 at the same time. Makes it a little bit more explicit than rather than relying on the CPU to do it implicitly. So you still have a lot of code you have to write. You might want to take advantage of even newer hardware. Vector 128 has been around since the 90s. Vector 256 was introduced around, 2011 or so. Vector 512 is more recent, around 2017 based hardware. But you're just adding more and more code to get more and more perf. That's where you want to say, well, what if I don't want to write all of that code? Or what if I don't know how to write all of that code? Because not every developer is going to go and learn all of these intricacies on how to do it. Well, that's where tensor primitives comes in. You can take all of that code, all 306-ish lines of it, and compress it down to this one line.
That's super cool. Okay, when you have the Solution Explorer covering this part, I was thinking, what's happening there? How big is that? or something. So, hey, this is the type of thing that we've been talking, and I really like that. You put everything there, the team created all of this, and I don't want to say that we don't care about that, but it's basically for us, it's just tensor primitive.zoom, and that's it. You don't take advantage of everything.
Well, and it's very easy to see the perf difference between it. If you've only got a few elements, you've got 4 of them, you're not really going to see any difference between the options. And in some cases, the biggest options even come with this minor penalty. It's slightly slower. But at the same time, you're working, this is 1.5 nanoseconds worth of difference. That's essentially 2 to 3 cycles, instructions being executed different for a standard modern computer that's running at roughly 3 gigahertz. Because 1 nanosecond is roughly 1 instruction cycle for a 1 gigahertz computer. And you're going to execute 1 billion of those in a single second. That's essentially nothing. Now, as you go up in size, the differences start showing. You start seeing, well, hey, some scalar's taking 86 nanoseconds, but even though I'm executing 32 times more data, when I start using some tensor, it's only taking 4 times as much, not 32 times as much. And as you get even bigger and bigger, these savings start getting more and more. And that's because we've taken the care to do all of the tuning to handle all of these edge cases about, well, how big is the cache on your computer? Am I going to be reading so much data that I'm going to throw away everything else out of the cache, and then I'm going to start having more cache misses? Am I best taking advantage of the hardware because it's got 512-bit support or 128-bit support? What if I'm on a machine that has 512-bit support, but it actually comes with a penalty to use it, like it downclocks your computer initially because it requires more thermal overhead? There's all these nuances that most people don't want to know or care about. And so we simplify it down to that one line for you, and it handles everything. And that reproduces across a wide range of machines, including other hardware. So this isn't just, even though I've only shown numbers here for Intel and AMD, you get the same performance optimizations on ARM. You get the same performance optimizations on WebAssembly.
Okay, hey, that's cool.
You get some, but not all of these optimizations on iOS and Android if you're using the Mono runtime.
I need to run this in my Raspberry Pi. I need
Yeah.
to give it a try and see how. I mean, not for the speed, but just to learn to do more. And hey, I really like it. And once again, line 307 is the winner of today.
Yeah, it's definitely the winner. But then we start getting into, well, what if I don't have that contiguous data? What if I want to work with data and not have to worry about that extra stuff? This one line is great if all you have is a single read-only span.
Yes.
But if you start having shapes to your data, you needed something a little bit more powerful, and that's where tensor comes in. And so the simplest thing is these two lines are equivalent to this one line. And the reason it becomes two lines is because you're declaring a shape to the data. And this is most obviously visible in that you see that there's multiple overloads, and that you have one that doesn't just take in the values, but you can also specify the length of the data.
Okay.
And so you can do this, and you can specify what's known as the strides of the data.
Yes.
Now, lengths specify how big the data is per shape. So the simplest thing to imagine is you've got a 1920 by 1080 image. So it's, you go 1,920 columns and then 1,080 rows. Now, computers, and this is even true in other languages like C and C++, they work in what's called row major order. So that means that the thing that has the biggest impact to the address comes first. And so even though a lot of people think of coordinates as X, Y, in practice, computers index as YX, because to compute the linear offset, you have Y times width plus X.
Yeah.
And so you end up having the data that way, and that's why this ends up being 1080 then 1920. Now, if you're just working with a basic shape, that's all you have to worry about is just the lengths. But when you start working with slices of data, you start having to think a bit differently. If you have a standard array where you've got 1, 2, 3, 4, all of this is sequential. And if you want to slice and you just want to take two elements, well, you can do that at any point. You can decide to take 2, 3. You can decide to take 3, 4. You could decide to take 1, 2. All of these are slices of the same data. You don't have to track anything special. You're still just sequential. When you have multidimensional memory like this, where you've got rows and columns, it gets a little bit different. Because what if you wanted to say out of a 4x4 matrix, what if you only wanted to take a 2x2 slice? So what if you wanted to take only the elements that I've bracketed here?
Yes.
Well, you'll note that there's two pieces of sequential data, and you've got this gap in here. And computers describe the shape of this data using what's known as a stride. So the stride exists per dimension, and it basically says, here's how far apart the data is. With a normal array, the stride is always 1 because the data is one element apart from each other. So if you wanted just this and you wanted just a 2x2 slice, but you wanted it out of something like a 4x4 matrix, well, then you have to actually describe what the underlying data allocation exists as. So you have to describe that column-wise, elements are one apart. So you've got one element between each other. But for rows, you have to describe the whole thing, that they're 4 elements apart. And so the stride says, even though I've got a 2x2 here, what I'm doing is I'm taking the first 2 elements here and then the next 2 elements here by describing how the data exists in memory. And that's what the strides allows you to do. So given a 4x4, you can take any 2x2 out of it without having to do extra things, just by describing these. And you can do things like that given even the full image, like a 1080 by 1920, by just doing tensor.slice. And slice works just like span, where you specify what the start indexes are. So I want to start at 0, 0. And what this is going to do is it's going to take this. And if I ended up saying I want to start at, let's say, 2, 2 instead, what's going to happen is it's going to say, well, here's 0, here's 1, here's 2.
You have there, yeah.
And then I'm going to go 0, 1, 2. And so it's instead going to take this section, because that's where I said I wanted the slice to come from. And so you're able to, it automatically does the stride calculations for you. It automatically determines how to track that data appropriately and allows you to work with it. And it allows you to do that and still get all the efficiency and performance improvements that this gives you.
What I like about this, and by the way, I'm going to go to the question. We have a couple of interesting questions in the chat, but what I like about this is that sometimes I get, this is kind of a natural way. When you say slice, if you know this domain, you know what are you doing, and I like to have this. Back on my NumPy and my Pandas days, the code, and I am not trash talking Python. I'm a huge Python fan also, but the code sometimes gets super tricky to understand, because you have this huge whatever where, okay, what did I did? Now it should be easier. Now I think, because it's like reading regular expressions. I am going to say, Copilot, explain this for me. So today I'm probably go back to my Python day and say, well, I can't remember what I did here, how I filtered this data. So explain me what I did there. But I like here that the concepts are there and we have the slides and other functions and more to work with this, because Zoom, this is slides, so you know you have this and you are going to work here. I really like it, and I hope that people are also getting, if they know, if they want to use it, there it is. Let me go back here to a couple of questions. So Runner Dude is asking about this. Are these implementations available online for reference? I will say yes. This is all part of the repo that we have, yes?
Yeah, so there's basically a few places you can find it. One, I've got the benchmark that I wrote, which isn't, they're still fairly naive and they're not necessarily showing the best code for each size. They're more meant to be demonstrative to show the example of here's how complex code can get. And it can actually get a lot more complex than that even. Something that a lot of developers aren't aware of is we have a website called source.net. Now that's source dot, then the word dot, then dot, then net.
It's tricky to share. Yes.
This is similar to the old reference source website that existed for .NET Framework, except it covers modern .NET, and it covers the core libraries. It covers ASP.NET, and you can just use it to search for anything. So if I just wanted to know how is int32 implemented, I could search int32 and easily see all the code for it. If I want to know how tensor span is implemented, I can do the same thing. Now, beyond all of that, there is also the actual GitHub. And the nice thing about source.net is it lets you find the code and then gives you a direct link to the code on GitHub. And so it allows you to go and browse the code, see the implementation, see the functionality and everything else, and allows you to actually go and, let's say you found a bug. Well, you can just go and log a new issue for us. You can open a pull request if you want to make an improvement. You can start a discussion with us if you've got a question that you feel can only be answered by the experts on the .NET team. There's also, of course, other community resources available. There's the C# community Discord, which I'm an admin on. There's the .NET Evolution Discord, which is for people contributing to the core .NET repos and code bases. And there's a number of communities out there that are hosted by various members of the .NET Foundation as well. And so there's lots of options to find these samples and to engage with us when you have additional feedback and nuance that needs to be given.
Yes, and I need to give some love to the Discord community that you mentioned. I haven't been there a lot, but I am part of the AI Foundry community, Discord channel community. We host office hours every week and more. And I like Discord. I spend my fair amount of time per day in Discord because it's kind of a natural conversation that you can have there and see what people are building and more. I'm going to also switch to the C#, but I am also going to invite everyone. Like, in example, we have a question right now from Philip. We did work with custom struct. If we can't answer that, because I know that we probably can't and we don't have time and more, Discord is usually a place that there are people from the team, there are experts here and there that they can help with these kind of things. So, hey, I like it. And yes, source.net is one of the trickiest one that I share the link in the chat for everybody, for everyone who want to give it a try. But I remember the first time I need to share this, again, playing my non-English speaker card, need to share and spell this URL. It was a fun moment. People saying, what are you saying, man? What is you mentioned 3 dots? Or no, it's not 3 dots, it's ... Hey, it's a fun one. Sorry, back to you, Tanner.
Yeah, well, to answer the question on custom structs, yeah, tensor is just generic. It takes in a T, and so it works with anything that is a T. You can put in any type there. You can make it a tensor of object. You could make it a tensor of int. You could make it a tensor of GUIDs if you wanted to. Not sure why you would want to use a tensor of GUIDs, but I'm sure someone has a reason out there somewhere. You can use any T and it works with it. Structs, manage data, etc. Now, one of the interesting things about this is we work closely with the language team, the C# language team. We work with the F# language team. And we frequently end up giving requests to provide better functionality. Given that we want to support any T, but we also have operations we want to support for specific T, because what you might want to do with a tensor span of int is not necessarily the same as what you might want to do with a tensor span of string.
Yes.
That kind of causes a problem because normally you can't expose API surface for one versus the other. Unless you start exposing extension methods. But extension methods have some limitations and everything else. And so C# 14 has a feature called extension members, which is basically extensions leveled up. You can now define properties. You can have extensions that work for very specific constraints. So you can have something that differs for a T that is an integer versus a T that is a floating point. You can actually have that difference now. And beyond that, we also ended up asking for a feature called extension operators. So you can actually define operators for specific T. So we can support, for example, tensor plus tensor on anything where the T supports plus itself. And we can do that via the generic math interface, addition operators. So we can end up defining, we don't have it in yet. The feature actually the features we needed just landed last night. And they got posted on various social media by the language team. But we will be exposing here for the next preview things like extension operator plus that only works for things that are addable. So now you can do tensor plus tensor for int and float and double and everything else without having to worry about all that nuance. And you don't have to worry about, oh, it's not going to work, or it's going to be available but then crash for string or throw an exception, because it just won't be available for string. We even have a new feature called user-defined compound assignment operators. So users could write, with normal integers, a user can write int x equals 5, and then they can do x plus equals 3. But you couldn't do this for your own struct type.
Yes.
With user-defined compound assignment operators, you can now define such compound assignment operators for your own types. Which means that we can also then specialize tensor compound assignment to avoid extra allocations, extra copying, and other things, because we're able to know, hey, I'm just overwriting the thing that's the input, so I don't need to go and create this new allocation and copy of data and everything else. And all of these features help make the not just tensor better, but the general ecosystem and all of .NET better, because it's available outside of just the things we're going to be using it for.
Yes, and hey, people are super happy with these extension operators and more. And I know that we are near to close, but I have Jose question started from the early beginning and more. And I don't know if we have an answer for this, but I don't know. Anyone in the team ever seen to create kind of a binding for TensorFlow?
One of the big considerations is that these libraries come and go over time, and even though TensorFlow was so big for many years, there's many features that have been removed or deprecated on it. It doesn't have the same support policies, and in many cases, they're being replaced in newer code bases by other things. I believe JAX is one of the things that's replacing TensorFlow in many modern libraries, and that's also provided by Google. Whereas TensorFlow was a Google project originally. Because of all of this nuance, it's not necessarily appropriate or right for the .NET team to provide official bindings, but anyone in the community is able to go and create their own bindings for any library they want. And if there are users, then they will come, they will use it, and it will be adopted. Not everything has to be or should be provided by the .NET team. Some things are really best provided by the community. And while many things won't take off, if they don't take off, it probably wouldn't have taken off if we provided it in the BCL either.
Yes, and a great example of that is the OpenCV libraries that we have, which are not, we don't create at Microsoft those, but it's super popular. I can't remember OpenCV Sharp. I can remember I was using one last year, and it's been there forever. It's nicely maintained by the community and more. But again, that's a very specific domain that we need to do that. Hey, Tanner, we are at the end of the hour. I like to be very, very sensitive with the time and everything. Thank you very much. This was amazing. Also, time flies. When I realized I want to see some code, it was literally 20 minutes ago. So sorry about that. And thanks everyone who are there. Tanner, thanks a lot. See you all next one in a couple of weeks. And hey, have a great day, everyone. Bye.